Okay, the next thing that we want to talk about is instantaneous velocity and instantaneous speed. Previously, we've been talking about average velocity and average speed, but what about the velocity or the speed at a particular instant in time? So let's talk about first the idea of instant velocity or instantaneous velocity. And so what we want to consider, again, I've drawn my little picture, I've got this curving path. And so you could imagine someone traveling through this path from A to B in a million different ways. They could start out going really slowly and then speed up. They could start out going really fast and then slow down. They could speed up and slow down, speed up and slow down. Again, there's an infinite number of ways you could go along this path from A to B. And so you could even do that a million different ways. And if you calculate the displacement from A to B and divide it by the time, you could have the same average velocity for a million different trips that were all very different from each other. And so we need some way of characterizing the velocity at a particular point in time. So what's the speed or what's the velocity it has when it's right here, or when it's right there, or when it's right there, any particular point. And so this is what we want to talk about. So just the idea of this taking the velocity or the speed of something at a particular instant in time, if you're caught speeding as you pass a semi-truck on the highway, the cop will not care that your average velocity for the entire trip was well below the speed limit. He's only going to care that when he was pointing the radar gun at you, he measured the instantaneous velocity of your car going faster than the speed limit, and you might get a ticket. So these are what we want to think about. So here we have that same graph that we used before, and we want to consider the point at point B. So the question is, what is the velocity that they have at point B? So you can think about it's the velocity that he has at this particular position when he passes this particular position, or when they reach this particular time. And actually, it's the time that is the important thing, because, so again, if I'm at this position here, the same position is available right here, because remember, we read the position off of this axis. So if I say, what's the speed he has at a particular position, well, I could say there or there. It's not clear which one I'm talking about. But if I say, what's the position when he's at a particular time, then that's unambiguous. So I've got a specific time here, and I can say, what's the position when the guy is passing at that time? And so that's what we want to consider as the velocity at a particular moment in time. And the way that we do that is we cut a smaller slice of time. So if instead of picking the entire time interval from where you start to where you end up, if you pick a smaller time interval, say from A to C, you can see that that's going to give you a better approximation of the velocity at B than going from where you start to where you end up. First of all, you can see that at B, the trajectory is in the positive direction, but if you consider the average velocity over the whole time, that would have a negative slope, and that would be, a terrible approximation for the velocity at B here. But if I go from A to C here, I can see that that would be much better than going over the whole time. And again, if I look at I've just sort of blown this up here. If I look from A to C, I can get my delta x, I can get my delta t, and I can calculate delta x over delta t, and that would give me the average velocity over that segment, which would be much better than the average velocity over the whole time interval. But if I went, instead of from A to C, if I went from that side of B to there, if I went over a smaller interval still, that would be even better. And the smaller that I can make my delta t, the more accurate my velocity approximation is going to be. And in fact, if we let delta t approach 0, so there's a rule, we can say this is, in calculus we say this notation, you say it's the limit as delta t goes to 0, but we let delta t approach 0 but not ever get there, so this time interval gets smaller and smaller, and what happens is this line slope, it actually becomes a tangent line that just kisses the curve right at B. And the slope of that line, that's what we say the instantaneous velocity at B is. And in fact, whether you're talking about 1 dimension or 3 dimensions, it doesn't matter. The velocity, the instantaneous velocity at any time is going to be the slope of the position time curve at that moment. And so that is a a very important concept. Now, if you've ever had calculus before, you might recognize this as the way of taking a derivative. If you don't know what that means, don't worry about it. This is just sort of an FYI for those who've had calculus before. But here we can see that we have the instantaneous velocity is the limit as delta t goes to 0. That's how you read that. And all that means is we're taking that time interval, we're making it zeroing in around b, and we're making it smaller and smaller, get it as close to 0 as you possibly can without it ever reaching 0. And that whole thing is written just simply as dx over dt. And in calculus notation, that's called the derivative of the position variable x with respect to the time variable t, or just the derivative of x with respect to t. And again, this is a vector, so we could note that that's going to be in the x-hat direction. But that is the way that we calculate instantaneous velocities, and generally you have to have calculus to be able to calculate the instantaneous velocity. But if you can figure out the slope of this tangent line, that will do the same thing for you as actually taking the derivative. So here is an example of doing just that. We have a curve. This is position versus time. Now, just to throw in a little wrinkle here, this is a vertical motion rather than horizontal. This would be motion along the y-axis. So this could be, for example, a ball that was thrown up, and so it's rising up, it's slowing down as it gets to the top, it stops, and then it comes back down and it speeds up on the way down. If that's what this curve represented, we could figure out what the velocity, the instantaneous velocity at point A and point C are by simply making use of figuring out the slope of these tangent lines. So the tangent lines have been drawn in here, and so here I have my delta y, and I can read this off the graph as 12, and this is 3, and so my delta y would be 12 minus 3. If I look at the slope for point A, I've got 12 minus 3. The time interval is from 4 to 0, so my delta t is 4 seconds. I plug in my delta y over my delta t. I get 2.3 meters per second. And you can see that the slope here is clearly in the positive direction. Now, at point B, you can see that that's basically where the thing turns around. So if I draw in a tangent line at point B, you can see it's just going to kiss the curve there, and it's going to be a horizontal line. So our line is going to be horizontal, the slope is 0, and so here we can see that the velocity is going to be 0. Now at point C here, we have the, again, the initial position is going to be 13. The final position is going to be about 5.5 if you look over from the graph. And so if you go final minus initial, that's going to be 5.5 minus 13. Then you're divided by the time interval, and you end up with, and there's a little mistake here, that should actually be minus 2.3 meters per second, because 13 is bigger than 5.5, so you're going to end up having this be negative. And again, you can actually see that this slope is negative, so that gives you the correct value. So let's look at example 2. Here I have a function. This is the position as a function of time. So again, what does that mean? I plug in any time period t, 3 seconds, 50 seconds, it doesn't matter. I plug in that value of t, and then I just calculate the numbers, and that'll tell me what the x position of that particle is at that time t. And so the question here is we want to determine the initial position of the particle and the average velocity between the times t equal to 0 and t equal to 5. And then we want to determine the instantaneous velocity at the time t equal to 5. So the first part of the question is to find the initial position of the particle, and what we mean by initial position is simply the position when the time is equal to 0. And so if I plug in t equal to 0 there, I'm going to have 0 squared, which is 0. That's going to make this whole term 0, because anything multiplied by 0 is 0. Same thing here, I've got minus 5 times 0, and I plug t equal to 0 there. And so I'm left with just 10 meters. And so the position x of 0 of t equal to 0 is going to be 0 minus 0 plus 10 meters. And that gives me my answer. That is the initial position. Now, how do we find the average velocity over the time interval t equal to 0 and t equal to 5? Well, what we want to do is we want to use the definition of average velocity, which is the change in position divided by the change in time. And so again, that's going to be the final position minus the initial. So it's final minus initial divided by the final time minus the initial time. Now we already know, we just did on the last slide, that the initial position, x at t equal to 0 seconds, and sometimes that's called x sub naught to tell me that that's the t equal to 0 position. We saw that was 10 meters. And so now all we need to do in order to plug into this formula, we need to calculate the final position, and that would be x at t equal to 5 seconds. And so I just plug in 5 seconds into my formula, and it was 2t squared minus 5t plus 10. I plug in my 5 seconds, I square it here, I have it just to the 1 power there, and so that gives me 25 times 2 is 50, minus 25, so that gives me 25, then plus 10, that leaves me with 35. And so my average velocity is going to be the change in position, which is 35 meters minus 10 meters, because again, that was my x naught. We're doing x final minus x initial divided by t final minus t initial, and that leaves me with 35 minus 10 gives me 25 divided by 5 meters per second. That would be the average velocity. Now, to find the instantaneous velocity, we can simply apply our formula for instantaneous velocity, which we know is simply that the instantaneous velocity is the derivative of the position function with respect to time. So we want to take the time derivative of our 2 meters per second squared t squared minus 5 meters per second t plus 10 meters. So we can take the derivative here, and so if I take the derivative of this, I'm going to get this 2 squared is going to come down, the power of t will be decreased by 1, and so I get 2 times 2, and that leaves me with 4 meters per second squared times t, and then here I've got t to the 1 power, that 1 comes down in front, doesn't do anything, but the power gets reduced to t to the 0 power, which is just 1, and so that leaves me with 5 meters per second. And of course the derivative of a constant is 0, so that 10 meters term goes away when you take the derivative. And so that gives us our generic velocity. This would be actually v as a function of t. For any time t, that's going to be 4 meters per second squared times t minus 5 meters per second. And so if I want to know what the instant velocity is at 5 seconds, I simply plug in that 5 seconds in for the t, and I get 4 times 5 is 20, minus 5 gives me 15. And so my instantaneous velocity is 15 meters per second, and that is at t equal to 5 seconds. If I picked a different time, I'd have a different instantaneous velocity. I just plug it in. But the key thing here is to, if you're given position as a function of time, and that would be our x of t formula, and I want to know what the velocity is as a function of time, the instantaneous velocity, I just take the derivative, and then once I have that derivative, if I want to know what the velocity at a particular time is, I just plug that time in and calculate it. Now we've been talking about instantaneous velocity. We can also ask about what the speed of an object is at a particular instant in time. That would be its instantaneous speed. And so we want to remember that velocity is a vector, and that means it has both a direction and a magnitude. So we can say that the magnitude of the instantaneous velocity vector, that's going to be found by dividing an infinitesimally small distance by an infinitesimally small time, and that's going to be the speed the object has at that point in time, the little sliver of time that we're taking. And so what that means, the long and the short of it is that the magnitude of the instantaneous velocity vector is the instantaneous speed. And so what that means is that if you're given a homework problem where you're asked to calculate the speed, you need to first figure out which kind of speed you're talking about, because you have now two different kinds of speed that you can calculate. You can calculate the instantaneous speed, which is the magnitude of the velocity vector, or you can calculate the average speed, which is distance over time. Now, which one are you going to use? Well, it's going to depend on what you're given in the problem. If you're given a distance and a time and you're asked to calculate the speed, they're probably talking about the average speed. And if you have calculated, or if you're given some velocity vector and you're asked what the speed is at that particular time, you're going to just take the magnitude of that velocity vector. But let's just note one thing. Speed will always be positive because a velocity vector can point in the negative direction, but the magnitude of that velocity is always going to be positive. And speed is either a distance, which is always going to be just a positive number. It doesn't make sense to have a negative distance. Or it's going to be the magnitude of the velocity vector, which is always positive. So our speed is always going to be positive. And again, our minus signs always tell us directions when we deal with vectors.